Okay, this lesson is optimization problems involving rational function models. So it's really word problems part 2. We're just upgrading the difficulty a little bit. The derivatives will be a little bit harder. The substitution will be a little bit harder. And there could be some continuity issues that we have to deal with, and maybe a quotient rule that comes along. But nothing too crazy here, just a slightly upgraded version of the problems we saw before. We'll also incorporate some measurement conversions in here, maybe getting closer to what real-world problems could look like, that measurement conversions might pop their head up. So let's take a look at the first one. Aaron and Tony are creating rectangular banners for the companies attending a convention. Each banner must have a colored border and a white center. The width of the borders will be 20 centimeters at the top and bottom and 15 centimeters along the sides. Because of the number of companies and the available wall space, each banner must have an area of 2.43 meters squared. What are the dimensions of the banner if the area of the white center is to be maximized? Well, there's lots to talk about, and I think the three big issues in this question is understanding what these banners look like, because they gave some dimensions of the sides and this colored border stuff that's going on here. Also, there's a major league measurement problem, and I want you to get used to this when you read word problems, whether it's in math or any of the sciences, is that when you're looking through a word problem like this, be watching out for the units that are in the question. See, I see centimeters there and centimeters there, but then I see meters squared there. So right away we know there's a conversion problem, is that some of the measurements were given in meters and some were given in centimeters. So we really want to be careful when we go to do this problem because of those different measurements. Now, the banner itself, and I'll deal with the calculus of this situation in a second, but this banner, and I'm going to try and do a little diagram of it here using what I can here in Microsoft Word. So I'm going to make a rectangle. They said it was a rectangular banner, so I'm going to get a rectangle going here and bring it down here a little bit. So here's my first rectangle, maybe about, that's a little bigger than I wanted there. Just tighten that down. So there's the colored border. I know it doesn't look like a border yet, but I'm going to insert another rectangle here. And that one, I'm going to change its color to white. So this will be the white center. This will be weird looking as I get it organized here, but when I'm done here, I think you'll sort of get an image of what's going on. So these banners that these companies are making have this colored border, which I'm going to exaggerate the size so I can write on it here, and a colored center. So that's what's really going on here. There's a picture of what one of the banners looks like. Now, there's lots going on here with the measurements and everything like that, but I'm just going to, I want to use all the space I can here, so let me just modify where that is. And I'm going to put these measurements on here. And I'm not going to get too excited about the meters and centimeters thing just yet, because during this lesson, I want to show you both ways, how to deal with meters and centimeters and measurement type conversions both ways. I'm going to go back to here, and I'm going to put on here, wait here. And the first thing I'm going to do is write on here these measurements. They said, okay, so the width of the border will be 20 centimeters at the top and bottom, which doesn't really match up with how I did it here, but that's okay. 20 centimeters here, the top and bottom will be 20 centimeters. And I'm really being careful with the units. You see, I'm writing the units on there. And then 15 centimeters along the sides here. So 15 centimeters along the sides here. And so that's the picture of what's going on here. So that's a little bit better for understanding what's happening with the banners here and all that nonsense about colored border and so on. Okay, so that deals with that. Now, the next thing I want to talk about is this meter squared thing. And when you get centimeters and meters like this, or any measurement where one is bigger and one is smaller than the other one, you have a decision to make as far as which one you're going to convert. Am I going to convert meters to centimeters, or am I going to convert centimeters to meters? And each one has its advantages, so there's not one that's better than the other, but I'm going to do it each way and talk about the advantage of each way. Now, squared measurements are a problem, and it's quite possible you haven't ran into any square measurements before, but I want to talk about converting squared measurements here. I'm going to convert this meter squared here. I'm going to draw another little rectangle. I'm just going to freehand this one over here. So here's a rectangle. And let's just, for discussion, say that this is a 1 meter square. Okay, so actually I'm going to erase that. I'm going to make it look more like a square. Okay, so back to here and a pen. Okay, and we'll keep the size reasonable there. Okay, so just a square. And I want to talk about 1 meter squared. And one of the difficulties that comes up in converting centimeters and meters back and forth when we're talking about squared measurements. See, there's 1 meter squared. This is 1 meter squared. And the question is, how many centimeters squared is that? And after all these years of doing measurement conversions in other grades, or maybe you haven't done a ton of measurement conversions, you might think 1 meter squared, well, that's 100 centimeters squared. But it's not, because 1 meter would be along this bottom here, what you'd get is 100. Now, I'm not going to have space to put 100 in here, but you can imagine that there's a lot of centimeters along the bottom here. And so that means a lot of centimeters squared along the bottom here. And so there'd be 100 of those little squares along the bottom. And then I'd have to go 100 this way as well. So it'd be 100 by 100. So when you're converting using squares, you have to convert both sides. So this 1 meter is 100 centimeters. So it's 100 centimeters this way. But this 1 meter is 100 centimeters going that way. So 1 meter squared is 100 by 100 equals 10,000 centimeters squared. So that's a really new thought when you're doing measurement conversions, is that based on whatever exponent you're talking about, here we're talking about squared, you have to do those conversions twice because you're converting each dimension. And what that means is this 2.43 meters squared is 24,300 centimeters squared. I like when I do that conversion like that, I like crossing out the old one, me personally, because then I know I've taken care of it. Now I've got this question all in centimeters, and now I don't have to worry so much, okay? Well, that's all the little details of this question. Now I can go back to this calculus plan I've got, which is our basic plan is to read the question and look for what is trying to be maximized here. So when I read through this question at the end, I see what are the dimensions of the banner if the area of the white center is to be maximized. That area of the white center definitely tells me that that's what I'm trying to maximize. So what I'm going to be looking for when I go to do this is area of the white center. So I'm going to go area of white center here. There we go. Area of the white center. Oh, that's gone back to pencil on me. Is length times width. But what length times width? That's the big question, is where to put the L and W in this question. Now, because I want to find the area of the white center, then I'm going to put the length and width on this picture, the L and the W, on just the white center part of that. And that's going to matter as far as how I handle this, but that's the equation that I'm going to take the derivative of, because that's what I want to maximize. At some point, I want to take that derivative. Now, the problem with this is that this has two variables in it, L and W, and to find derivatives of two variables makes a really big mess. And if you can get rid of one of the variables, it makes your life significantly easier. Well, how? Is there a way to get rid of these two variables? And the answer is yes, because they told me that this whole banner, each banner, must have an area of not 2.43 meters squared anymore. No, 24,300 centimeters squared. So I'm just going to go over on the side here. I really like doing this kind of work off to the side because it reminds me I'm doing side work. I'm not really doing the question over here. I'm just doing the side work it takes necessary to be able to do this question. And this side work says, oh, that means that the whole banner, which would have, let's see, its length would be L plus 40. See, this is the whole banner is L plus 40. And then its width, its whole width of this banner would be W plus 30, see that's all the way across here, the whole banner, W plus 30, we know what that has to come out to be. That has to come out to be 24,300. And I'm not worried about the units anymore because I know I've got it all in centimeters. And so now I've got the equations I want. I definitely want to work on this one over here. Here's the one I want to take the derivative of over here. But here's the one that I'm going to use to get rid of either L or W. And you got your choice here which one you want to go after. I'm going to go after the L. And so to get the L, I'm going to go L plus 40 equals 24,300 over the W plus 30. That's the easiest way I see to be able to isolate L. And so then I get L plus 40. Oops, not L plus 40. We don't need L plus 40 anymore. I'm going to move that 40 over. Here we go. Is 24,300 over W plus 30, and then subtract the 40. So I'm going to write but over here. But, and then I did some work over there to tidy that up. So that's my side work. Now, what that means now is I can go back over here and go area of the white part of the banner is equal to the length, which is 24,300 over W plus 30. Subtract 40, and that's all times the width, which is just W. Now this equation makes me very happy, and the reason it makes me very happy is that it is now all in W's. That'll make taking the derivative a lot simpler. Now it's not ready to take the derivative. Well, I guess you could do a product rule here, but I'll stick to what I've said before about derivatives. If you can multiply out some stuff before you start fairly easily, you'll probably find that easier to do. So I'm going to multiply that W in, and I get 24,300 W over W plus 30 minus 40W. And this is sort of how this day's word problems are a little bit more difficult because they've got some quotient rule in them. Compared to some of the quotient rules we've done, this isn't the worst that we've had to deal with. So now I'm going to take the derivative. So the derivative of this, okay, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. And then the derivative of that second, that minus 40W is just minus 40. And I'm going to tidy that up just a little bit. That is the 24,300W. When I multiply that in the brackets, it immediately will subtract 24,300W because there's that other piece there. And you can do it in multiple steps if you want, but I can sort of see what's coming here. Area of the white prime equals, I just get, 24,300 times the 30 is 72,9, and then 3 zeros now over W plus 30 squared. Minus 40. And if you need to multiply out those steps, you do it. But I think you'll see that 24,300 times W from the first brackets minus the 24,300W from that second term, those will cancel. So that's the area of the white prime right there. Now, for max min, set area of the white prime equal to 0. So what I get is 0 equals 72930 over W plus 30 squared minus 40. Now, this is sort of an awkward solve if you haven't seen too many of these before, because all these methods we've used before of isolating, factoring, and so on, there's lots of things you could do here. And one of the things that might come to mind is a method that we've used many times before, which is multiply through by the common denominator, multiply everything but W plus 30 squared. And you could do that, but I want to show you something else here, is that if I bring, when you've got only two terms like this, if you just bring one of the terms over, then you can cross multiply. And really the same sort of steps as if I had just cleared everything and multiplied by W plus 30 squared. But that gets rid of that denominator there because I just brought it over and multiplied by it. And so then now I can, let's see, W plus 30 squared equals 72930 over 40. And I could simplify that, but I know I'm going to use my calculator here anyway, so I'm not going to worry too much about it. So I get W plus 30 equals plus or minus the square root of that big mess. And then I bring the 30 over, and I get negative 30 plus or minus square root 729,000 over 40. So when I get my calculator out, and if I go negative 30 plus the square root of 72, 9,000, 72900 over 40. And when I type that in, I get W equals 105. The other W I get is negative 165 when I punch that into my calculator. And clearly that's not admissible. We can't have a width of negative 165. And this happens a lot in squared type questions, that we don't have to worry about any negative answers because we're looking for a W that's positive. So we're in great shape here, that we've got W equals 105 here. So is that the right answer? And we talked about this in the previous lesson, that we better check to make sure that this actually maximizes the area. That's what we want to do, is maximize the area, because we don't want to minimize the area. So this is where we build our little chart. And so we go over here and we go, okay, the two sections I want to look at are 0 less than W less than 105. And why am I using 0? Well, there's two reasons why I'm using 0. But the most important one is that the lowest the width can be is 0. So that's the lowest I want to talk about. And then I want to look for greater than 105. And I'm really hoping that something's going to happen here, but I won't prejudge what's going to happen here. I'll just write in there. And then my area of the white prime is, where's my derivative? Well, there it is there, but I'm going to look back up on the previous page, is 72900 minus 40 over W plus 30 squared. Oop, no, I just wrote that over top of the fraction. It's not actually over top of the fraction, is it? So let me just get my small eraser out and clean that up a little bit. Oh, that works good. And then back to my pen. So this is 72900 over W plus 30 squared minus 40. Now this one, not so easy to sub into. That is, you're not just going to be able to look at this using the positives and negatives. I don't think, probably. Maybe you can, but for most people, I think what they're going to do is they're going to choose a number between 0 and 105, say about a 50, and you're going to sub that into that whole thing. And what you find out is you get a positive number in there. And then if you choose something above 105, say like about a 120, whatever number you want to choose there, and sub it into that whole thing, I think you'll find you'll get negative here. And what that means is this derivative is going, area of the white prime there, is increasing, and then it becomes decreasing. The name we give for this is the first derivative test. The first derivative test is when we build a chart to find out what the derivative is doing. And then that confirms that there's a max when W equals 105. That makes us feel good that we found the maximum here. So therefore, answer the question, therefore the banners should be, now be careful here, 105 is the width of the white part here, back up to here. This here, and I'm going to do it in red here, it's just right in here, is that this should be 105, this width right there. But it says, what should dimensions of the banner be? We got to add the 30 centimeters on there. So the banner should be, back to my other kind of pen here, 135 centimeters. That's the width. Now the length, how am I going to get the length? Look back through here. I know that W should be 105. How am I going to get that length? And all the way up here, and this happens a lot in these type of questions, you got to go back and find the equation for length, and it's right there. See that length equation there? That gives me the length I need. So I'm going to go back here and go, just a little side work here. L equals, what was it? 24,300 over 105 plus 30 minus 40. And if you type that in your calculator, I think you'll get an L of 140, which is awfully tempting to write in there, but that's not, that 140 is this L here. That's why these word problems are a little bit more difficult in this section. That L is this 140. They wanted the length of the whole banner, so I got to add that 40 in there. So that length is actually 180 centimeters. So there's my statement there of what the length and width of the banner should be. Notice that this question did follow the same pattern as the previous word problems, is come up with, and I'm going to write them in steps, come up with an equation for what you want to maximize. Do a little side work to get it down to one variable if you need to. Take that derivative, set it to 0, and build a chart. and finally answer the question. So you got to use your brain in step 6 here. And I don't know, you think you have to memorize steps 1 to 6 here. I'm just trying to keep reiterating that the word problems in calculus have a sort of rhythm to them, and that there's a same plan that you'll often use to get these things, is that you'll find an equation for what you want to maximize or minimize. You'll take the derivative and you'll set it to 0, and you'll build a chart, so that pattern sort of follows through each time. Okay, 2 more examples, and then we'll be done. Helena is designing a cylindrical can. The can will hold 280 milliliters. Right off the bat, milliliters. We got to talk about milliliters. So we're doing this unit thing again. We're keeping an eye on the unit. The metal for the side of the can will cost 0.75 per meter squared. Yee. Okay, so we're already in trouble. We got milliliters and meters squared. The metal for the top and bottom, which is thicker, costs $1.40, $1.40 per meter squared. The side of the can is 1 rectangular sheet. The circular top and bottom are stamped out from a rectangular sheet. The unused metal from the rectangle is donated to charity. What? What are they talking about? Okay, we'll get to that in a second. The charity exchanges the scrap metal for money. What dimensions for the can will minimize the cost of materials? If you've been sort of following along with these examples, all those details as you're reading it, don't freak out about those. Get all the way through and get to this. Minimize the cost of materials. That gives me a huge hint on what I'm going to do in this question. And what I'm going to do in this question is try to find an equation for the cost of this can, and then I'm going to try and take the derivative there. But there's a lot of details that are hard to follow if you haven't seen one of these questions before. So let's just get a little work here. Let's get, does this thing have a cylinder going for it maybe? Oh, it does. Look at that. Okay, so cylinder. Oh, it wants it way up there, so I just take a second and move it down to where I want it. But I've got a nice cylinder here to look at. And I want to talk about cylinders for a minute because it's going to take a minute to understand all the details here. And the first thing I want to talk about is when you're designing cylindrical cans, I mean, you never really thought about it maybe before, but a can like this, if you're going to store things in it, the top and bottom better be a little bit thicker than the sides, just to make sure the pressure of things being pushing down in the bottom of the can, it doesn't push things out. I think about sometimes you get a drink at a fast food restaurant like a Coke or a Pepsi, and that bottom better be good. That bottom better be made of something a little bit solider than the sides, because you don't want the bottom to come out, because it's going to have the most weight on it, whereas the sides don't have quite as much weight. So that's why they're using a slightly thicker metal here, and that's why the metal on the top and bottom costs a little more. So that was that detail that they mentioned in there, that the top and bottom costs a little bit more than the sides. Now next, how are these things made? Now I want you to think about if this was truly a cylindrical can, maybe a soup can. I don't know if you've ever done this before, but if you take the side of a soup can, like the soup can label off, and you pull it off and you roll it out, it's just a rectangle. See this piece around here, that goes around like this, around the outside of the can, that's a rectangle. It's just a rectangular piece that goes around the outside. So when we go to talk about how did they build this can, when they go to build the side's just going to be a rectangle. And I'm going to go back to my rectangles here because they were the same color. And I'm going to put a rectangle right beside it. And when I mean right beside it, I mean I really want it to be sort of the same size so you can see that side is rolled around like this, and that's the side of the can. And what I mean by that is you roll that can out and you get this soup label. So this soup label here, well, dimensions-wise, will have a very similar dimensions to this can, which has a radius of R and a height of H. So the height of this label, this soup label, the wrapping, we call it the lateral surface area of the can, will have the same height as the can. Now, its width, though, is the wraparound, is going all the way around here. So that's the circumference, which is 2 pi r. So finding the area of that sheet for the side, and I'm going to label that's the side of the can. It's not too bad, actually. Pretty straightforward stuff. And actually, if you ever saw the surface area formula for a cylinder, I'm going to write it up here. Surface area for a cylinder is 2 pi r squared plus 2 pi rh. There's the side of the can right there. Well, that whole time, we were just finding the area of a rectangle. So when I go to build my cost equation, I'll just use that area for the area of the side of the can. Now, this other part, though, the top and bottom, they said something different, and it's sort of weird. It's going to take me a minute to build it here. They said that the top and bottom was stamped out of a rectangular sheet. What do they mean by that? So let me just get a rectangular sheet here, and I don't know if I'm going to build this the right length or not. I'm going to have to play around with it for a second because I'm going to have to insert a couple of circles here. Circle, oh, that's not going to be the right color. We'll go to... Oh, and wow, I think I did a pretty good job making it the right size here. But I'm going to need another one of those. So let's just copy that and paste it. There, I got my other circle. Let's see how I did. No, I didn't make it wide enough. Okay, so I got to make this wider. Actually, it'd be easier to make it smaller afterwards. It's actually pretty nice. It's a little bit slow, but compared to my actual drawing, this is way better than I can draw. So let's just tighten that up. So this is one way to build the top and bottom of a rectangular can, is you go, okay, take a rectangular sheet, and that's what they were saying in the question, take a rectangular sheet and then just stamp the top and bottom out of it. So you just punch the top and bottom here. And this is sort of what it would look like when the whole process was done, is you'd have this leftover piece and you'd have stamped the top and bottom of the can out of here. And the question is, how much metal do you need for this extra sheet here for the top and bottom? I'm going to label that. This is the top and bottom. Well, okay, so we do have these circles on here. So take a look here. The top of these circles still do have radius r. And so what that means is we'll need a rectangular sheet that's 2r in height. And then it will be, let's see, 1, 2r for the first circle, 3, 4r for the second circle. It'll be 4r this way. So when we want to find the area of the rectangle that we need for this top and bottom to stamp out the circles, it'll be 2r by 4r. Whew, that was a lot of work just to understand the question. Anyways, now we get down to the cost equation. Cost equals, okay, so the area, okay, I'm going to make a mistake here. I'm going to leave something out here so we can talk about it afterwards. The area of that sides is 2 pi RH. That's that rectangle up on the top right there. And then these other rectangle, and I'm going to leave some space there because I'm obviously leaving something out, would be 2r times 4r, length times width of that second rectangle. But that's missing a detail. That's not the cost equation. That's the surface area equation. If you want the cost, you got to multiply each of those areas by how much they cost. So this first one was 2 pi RH was the sides. How much did the sides cost? 0.75. So that needs a multiplier of 0.75. And then this other one, the top and bottom, it costs more. The top and bottom costs $1.40. So I'm just going to simplify that up a little bit, and I think I get 1.5 pi RH plus, let's see, 2 times 4 times 1.4 is 11.2 r squared. And it's a pretty nice equation, but it's got the same difficulties that other equations have had, which is that it's got two variables in it. So we're in really good shape here. We've got a cost equation that we want to take the derivative of. However, it's got both r's and h's in it. So what I'm going to go back is look at the question and see if there's some other details here, because they do give us another detail. Let me read through. The can will hold 280 milliliters. So I know that the volume has to be, so here's my side work here. I always write but. I don't know why I write but over here, volume has to be 280 milliliters. Well, milliliters isn't meters. Like everything when I go to use this, when I use this stuff, I used meters squared. So I got to get this 280 milliliters over to meters somehow. And here's a little detail. Maybe you don't know unless you took a lot of chemistry, is that milliliters is the same as centimeters cubed. Well, that's fine. That's still not meters. To get to meters, we've got to take centimeters and divide it by 100. But because it's power 3, it means that you got to divide by 100 for each of the length, width, and height dimensions. That's what I was talking about in that first problem, is you got to divide the first centimeter, the second centimeter, and the third centimeter if it's centimeters cubed. And in the other one, I went from the big measurement to the small one and ended up with like 24,300 or something like that. And so if you like working with the big numbers, you can do that. In this example, I'm going to switch over to the other way and go to the bigger measurement, which means smaller numbers, if I'm going to go for the bigger measurement. And if you multiply that out, I think it's 0.00028 meters cubed. So that's a little awkward to carry around. It's not the worst, but it's a little awkward to carry around. So generally speaking, me personally, I always go to the smaller measurement, which gives me the bigger numbers, because I find those easier to use. But, you know, I want to do it both ways so you can see it. Because this one, we're sort of stuck here. It's a little bit more difficult to convert the meters squared here to centimeters squared because of the fact that it's dollars per meter squared. So sometimes you're sort of stuck. Anyways, now I'm home free. Well, I'm not quite home free because I didn't leave enough space here, or I overdid it on the old explanation there. I need a little bit more space here because that volume means that pi r squared h, which is the volume formula for a cylinder. Let me write that up here. Pi r squared h. If you're wondering about formulas for the upcoming test, I'll always give you the geometric formulas. I mean, if it's a triangle, maybe I won't feel like giving it to you, but here I'll definitely give you those formulas. And so I'd like to solve for h in that thing. You've got your choice. You could solve for r squared, but then the equation I'm working with has r and r squared in it. I don't think you'll find that as easy. The h is a little bit easier to deal with here, so it's 0.00028, and that's all divided by pi r squared. So now I can sub that in, and I can get C equals 1.5 pi r 0.00028. And if you're frustrated by all those zeros and writing those a bunch of times, then maybe you should go to, whenever you can, go to the smaller measurement, which will give you bigger numbers. So I'm going to tidy this up. C equals, let's see, 1.5 times 0.00028. I actually end up with 0.00042. Oh, the pi's cancel. And I get r to the negative 1 because r and r squared, 1 subtract 2 would be negative 1. And then I get plus 11.2 r squared. Don't have to do anything with that term. And actually, that's ready for derivatives. That's a good cost equation because it's all ready to take its derivative. I just sort of got lucky in the way that all played out, that it was ready to take the derivative. So then I take the derivative. I mean, that was my plan the whole time, was to work this through so I could take the derivative. So C prime equals negative 0.00042, r to the negative 2, and this is 22.4r. And these are difficult to solve. You could multiply through by r squared here. Some of you might see that move. 4 max min. Set C prime equals 0, so I get 0 equals, I'm going to tidy this up as I go, negative 0.00042 over r squared. Equals. Plus 22.4r. And there's lots of ways to handle this. Like I was starting to say there, is you could multiply through by r squared here. That would totally work. I, generally speaking, I just put one of them. If it's only two terms like this, I just get one on one side and one on the other, and then I cross multiply here. So I'll get 22.4 r cubed equals 0.00042. And once I've got that settled out, life's a lot better. So I'm going r cubed equals 0.00042 all over 22.4. And this is a cube root, so I don't have that plus or minus thing to worry about. And if you punch that in your calculator, I think what you get is 0.0266 meters. So don't let that small number freak you out. Because remember, we converted everything over to meters up here. Yeah, so now that's in meters, but you might feel better converting that back to centimeters, 2.66 centimeters. I'm getting ready to answer the question here. Oh, I've got to do my chart here. Okay, hang on, I got to do the chart. Because we don't want that to be a minimum. We want that we want that to be minimum. We don't want to maximize the cost. We want to minimize the cost here. So now I do my chart. I do R, 0 less than R, less than, careful now, 0.0266, and then R greater than 0.0266. 0.00266. If I'm going to use that old equation of meters, I've got to use my meters for this, and this is C prime. And this is awkward, these subs in there. And you'll find in the test, not every question do I ask you to verify it's a max, because it's just too time-consuming on the test. So on some questions, I'll say, verify the maximum. And other questions say, you don't need to verify the maximum here, or minimum in this case. But if you sub in a number between 0 and 0.0266 into this derivative here, this C prime derivative here, you'll find that it does what you need it to do. It does negative, then positive, so it's decreasing, and then increasing here. So it's a minimum at 0.0266 meters, which I'm already converting that over to 2.66 centimeters. Now, how do I get the height? Because the question said, let's make sure we answer the question, what dimensions for the can? So therefore, the dimensions of the can are R equals 2.66 centimeters. And I wouldn't mark it wrong if you wrote R equals 0.0266 meters, but you know, I think most people want that in centimeters so they can get a perspective of what's going on here. But we want the height as well to get h, so we look back, and it's always there somewhere. If you look back through, you'll have an h equation. That's one nice thing about these questions, is that somewhere along the way you had to find h anyways. So then to get h, I get h equals, where'd it go? I lost it already. 00028 over pi r squared. So pi times 0.0266 squared, and I get h equals 0.126, but that's meters. So, and h equals 12.6 centimeters. And again, you could answer it in meters, but I think centimeters makes a lot more sense here to give an answer for it. That is a very popular question. That's often the question we choose on the test, because we sure like the cylinder ones, and sometimes it's cut out of a rectangular sheet like that, and sometimes it's just you have to do the two circles separate, but a great question. Last one for this lesson. On the highway, a truck burns fuel at a rate of, well, that didn't appear right. It's I think it's 0.003x plus 3 over x. Liters per kilometer when its speed is x kilometers per hour. Fuel costs 65 cents a liter. Well, that tells you how old this question is, doesn't it? 65 cents a liter. It's more like $1.40 a liter now, but okay, so that's fine. 65 cents a liter. Maybe this truck company gets a deal on fuel. The driver's paid $16 an hour. Okay, well, that totally gives the question away, doesn't it? No truck driver's making $16 an hour anymore. What steady speed will minimize the operating costs for a 400-kilometer trip on a highway where the posted speed limit is 90 kilometers an hour? Interesting little detail there. Posted speed limit is 90 kilometers an hour. Okay, well, this one's different than the other ones. It doesn't have a lot of substitution in it. It's got some thinking about the cost. So I want to walk through this carefully and talk about what are the operating costs for this truck. And the costs are made up of two things. And I'm not going to do it with letters yet. I'm just going to make a word equation. There's going to be two costs for this. There's going to be the cost for the fuel, and then the cost for the driver. And so to get cost of fuel, we need the amount of fuel times the cost per liter. That's going to be how we're going to get our cost for our fuel. And then the cost for the driver, we're going to do hourly rate times number of hours. Seems pretty simple. And I'm trying to do these word equations one little step at a time so each step doesn't seem too difficult. Now, cost per liter we know, but amount of fuel, to get the amount of fuel, we need this equation, this weird thing they showed us here, this weird, I'm going to highlight it. They said this truck uses 0.003x plus 3 over x liters per kilometer. So the amount of fuel is going to be how many liters per kilometer times the number of kilometers. That's going to be the amount of fuel times that cost per liter, which is the completely unreasonable 65 cents a liter. Now, the cost for the driver, well, okay, his hourly rate is $16, and I got to multiply that by number of hours. Well, that's going to be his distance divided by his velocity. And I've used these little multiply symbols here as my word equations. I better get away from that now because I'm going to be using some x's. So I'm going to start putting everything in here. The liters per kilometer, they told us, was 0.003x plus 3 over x, a weird little expression for liters per kilometer. Then it's times the number of kilometers. Well, they told us how many kilometers. That's the good news. It was a 400-kilometer trip. And then times the 0.65, whereas the cost for the driver is $16. Now the distance is 400, and the velocity was the speed, which is x kilometers per hour. So that's over x. Well, now that's a good equation. And sometimes that's all you can do is build a word equation that makes sense to you, and then try and maneuver it into a word equation that you can use for the question that was given. This actually, the derivative part of this question is a lot easier than the other ones because this is all x's already. The creation of the equation is a little more mysterious than the other ones. I'm going to multiply out these brackets here. 400 times 60.65 times the 0.003x. If you multiply that all out and you get your calculator out, I think you'll find if you multiply all that out, what you get is 0.78x. And then the other one, 400 times 65, sorry, times 0.65 times 3 times the x, the over x, I think you end up with 780x to the negative 1. And then this one over here is 400x to the negative 1. I'm getting ready for the derivative there. If you got to write it as 780 over x first and 6400 over x first, that's fine. But this is my final cost equation, 0.78x plus 7180x to the negative 1. That's a good cost equation that I can take the derivative of. So I get C prime equals 0.78. And this is what I was talking about, this one having the much easier derivative than the previous ones. Negative 7180x to the negative 2. 4 max min. Set C prime equal to 0. Oh, got a little problem here that I got to deal with. 0 equals 0.78. minus 7180 over x squared. I'll bring that over. 7180 over x squared equals 0.78. Now we'll see if I can fit all this in here. 0.78 x squared equals 7180. Bring the 0.78 over and square root it. I get x equals square root 7180 over 0.78. I don't need plus minus here because I'm talking about the velocity of a car, or sorry, of a truck, so I don't really need to worry about the negative here. And I get x equals 95.9 kilometers per hour. That's the speed that they suggest. Now, we should check if that's a maximum, but I think you'll find if you go 0 less than x less than 95.9 and x greater than 95.9. And I pump that all into C prime. If you select a number between 0 and 95.9, what you'll find is it's negative, positive, so this is a minimum. So that will check out. Minimum. There we go. The question is, how fast should you drive here? Because it says the posted speed limit is 90 kilometers an hour. On a math test, I would accept the answer of 95.9. I really would. because that's what the math tells us. But in the real world, we might have to incorporate the danger of us telling our truck drivers to drive over 90 kilometers an hour to minimize our costs. Because what happens if they get a speeding ticket? Or what happens if our insurance goes up? Or what happens if they get in an accident and get charged and we have massive liability here? So I guess probably I would tell you that 90 is the right answer here. Tell the truck drivers to drive 90. We'd like them to go 96 to minimize cost, but 95.9. So let me just put that both answers. Therefore, the truck drivers will minimize costs at 95.9 kilometers per hour, but should drive 90 kilometers per hour. You know, and you say, well, shouldn't we just said 90 at the start? Well, no, the answer could have been 85. We might have got an answer of 85 kilometers an hour, in which case, even though the speed limit's 90, we'd still tell them to drive 85 to save us money. Or maybe we wouldn't. We'd say maybe we'll tell them to drive 90 and keep traffic moving. I'm not sure. That's sort of the real world version of this problem, and that's something that the business owner would have to decide. I mean, as the math person here, you'd say, well, 95.9 is the best, and then you can choose from there. Okay, so I think we've completed those three questions nicely. The key component of word problems is practice, and so we say this all the time in math. It's not good enough just to watch these word problems and go, oh yeah, I sort of get it. You really have to practice and land them yourself and figure out all the little details yourself. So make sure you take a good run at all this homework and have a great day.